So. Yeah, here we are. And it's already on, huh? So be careful, don't swear.
All right.
Do you have a microphone? Do you have
A what?
A cell phone in your pocket?
Yes. Not anymore.
Okay, can everybody sit down, please? Okay, welcome back, everybody. We are here with Adam Hitchcock. He works for DISQUS, and he works on making DISQUS real time. Thank you, Adam.
Thank you. Yeah, I'm Adam Hitchcock. Came from San Francisco for this, and it's great to be here. It's an awesome city. Supposedly this is an advanced talk, so I guess that means I put code in it, so there's code in there. And I hate long talks, so I'm going to try and make it quick so we can do more questions. I think they're more interesting. And I have a tendency to talk quickly, so if anyone has any problems, just yell at me and I'll slow down. So what is DISQUS? We're a community platform. Basically, we make it so you can have an instant community on your website. The primary product is a JavaScript embed, so line of JavaScript, and you get comments on your web page. The backend for all of this is primarily Django and is powered by Postgres. When making the real-time system, we decided to depart from that and make a separate service. So it is an entirely separate infrastructure from the core DISQUS app. So if you've heard anything, previous talks by other people like David Kramer, big departure in terms of architecture and everything. Why do you want to do real-time? Well, you want to do real-time because getting information to your users as fast as possible is a good thing. Information sitting on your servers is like unshipped inventory in a warehouse. You're not making money off of it. So you want to get it to them. You can increase the engagement of your users with your product by making it like sparkle and stuff in real time. It looks great. Personally, I think it looks great. And then another thing is, aside from our consumer product, we also can sell it as a kind of a B2B product where we have a fire hose similar to other companies like Twitter where you want raw access to everything that's going on. So, and also just one definition, we call real-time less than 10 seconds. My personal goal was to make it less than 1 second, so that's just what we consider real-time. And this is a little demo of what real-time looks like. in the product. So you can see as comments come in, the little yellow highlights will show up, and you'll see like, oh, look, someone is typing. It says is typing there. So typing notifications, new posts, votes, and likes on threads or thread votes. So they come in, look, new replies, yay. All right, so that's what the end result looks like. So I asked the audience a few questions in this talk, I guess. So if I ask the audience a question, how many of you will raise your hands? All right, about 2/3. Okay, so I'll use that to gauge engagement. So how many people are actually using real-time in your product or for whatever right now? Okay, and we'll scale that up a little bit. Okay, cool. So do we, it turns out. It's actually available right now. The video I just showed you is of a product we're rolling out currently. But previous to that product, we had another real-time system. It was basically memcache. So when something happened, we would set a key in memcache, and then the embed, the JavaScript, would just pull that key every 5 seconds. And this was kind of fail scale for us. It just couldn't handle the load of the entire DISQUS network. So we could only expose this to either sites that paid for the feature or a set of registered users. And we really wanted it for everyone. Because this is, everyone. That's a lot of people. And it would be great to give it to all of them in real time. So I made realtime. It's currently available on all of the new product sites, DISQUS 2012. And we're also currently still testing on a subset of our network because it's not done yet. This is a work in progress. We have seen a maximum level of concurrency of 1.5 million concurrently connected users. So that's like open connections. That causes about 45,000 transactions or new connections per second. At a different event, so the website IGN used real-time to power the conversation for when they were doing that E3 live stream. And during that stream, we saw a peak delivery rate of 165,000 messages a second. So that's like posts getting delivered to end clients of new messages. And the whole system has about 0.2 seconds of end-to-end latency, which is just the real-time system. That doesn't include any latency in the Django and database layer. Let's see. So how did we do it? We use Node.js and MongoDB, right? No, this is a Python conference. All right. We used gEvent, gUnicorn, Flask, and Thunk. Who knows what the top 3 are? Okay, all of you. Excellent. Engagement's rising. This is good. All right. Does anyone here know what Thunk is? It's a new library. Okay. It's made by a company called AndYet, and it's basically a queue on top of Redis. And a lot of people would say, well, why would you do that? Redis is a key value store. Yes, but it was really easy at the time, and it turned out to exceed my expectations, so we stuck with it. Basically, I was having trouble getting an actual queue set up. So this was my hack for the day, and it was great. I'm really glad I made the decision. And then on a system level, we're using Redis, again, for a queue, as well as Redis PubSub. Who knows what Redis PubSub is? Excellent. Okay. Nginx, which is a web server, and HA proxy, which is proxy. All right, the architecture overview. So there are 3 kind of main data flows in the real-time system. So the first is, how does new data get into the system? Then there's how do new requests that want that data get into the system? And then how do we connect the data to the people that want it? So the first part is kind of this upper left-hand corner. So it starts off when someone's sitting at their computer. It's, oh, someone was wrong on the internet. I need to correct them. So they type away and they click post. And that goes into the Django app. We have a post save hook on various models. That goes into the Redis queue, the Thunk queue. And then that goes into what I call the backend. It's a very original name. And that's basically a G-event server that does stuff, and then it puts it into Redis pub sub. So that's your kind of first flow. It's a kind of a data pipeline. The second one is you have Nginx HA proxy, so requests are coming in through those, and then they go into a Flask web server, and they, we have a streaming request that goes out. And then in the front end as well, there's another little pipeline that's listening to Redis pub sub, marshalling that data to the appropriate requests. So a little bit, I also want to talk about the hardware architecture. So the backend servers, we run one process per core, and we have 2 machines doing this. It's actually it's a pretty lightweight task. So we have like 8 processes or something of it across 2 machines. And why 2 machines? High availability. Kind of. One can fail, so that's not bad. In the front end, we have 14 front end nodes. They're 16 cores each, I think, and have lots of RAM and all the things. And they run at a way more CPU. They're doing a lot of work because there's a lot of requests, and those are the expensive things. So separate clusters. And then there's also another Redis cluster of like 6 machines or something like that. All right, so inside of these things, so again, we got the DISQUS app up there. This is the pipeline of the backend, formatter, multiplexer, publisher. I'll go into that next. Then in the backend, we have this listener, then a subscription pool that does the marshalling, and then requests layer thing. And I'll go into that after the backend. Again, original names. So this listens to the Thunk queue. The formatter is what's doing the listening. It's basically each of these boxes is basically a while true loop, and there's just the arrows are Python queues. So it's while true, listen to a queue, do something, write it to a queue, and it's a nice little pipeline that data flows through. So formatter cleans formats messages. Any missing data, it does it. It will fill it in. It will be, oh shoot, you need this thing. I'll get it from the database. But that's kind of like last resort. It turns out always all the data is there. This is the final format. So at this stage in the pipeline, we already have the message completely formatted for the end publication. Originally, we did not. And it turns out when looking at, so if you look at the data space, or the usage model, I guess, of consumers of our product, we've got millions of installed DISQUS JavaScript things. And it turns out most people don't read my blog. In fact, I don't know if anyone ever has. But a lot of people read CNN. So we have this very heavy-tailed distribution of lots of idle sites and a small number of super popular sites. And these super popular sites will have tens of thousands of people looking at them at once. So it turns out when we were doing some testing, we immediately found that everything broke when we tried to do JSON formatting in the front end. You're like, oh, it's 1 million people look at this now, and you don't want to JSON format the same thing 1 million times. So moved it back. And this was a lesson that we really applied to everything. What's the earliest you could do this? We are also experimenting with compressing the data at this thing. gzip's the exact same thing. It's actually harder than JSON compressing. So we want to do that as early as possible too. But it's difficult to gzip early and then stream to multiple clients. But we're confident we can do it. Anyways, multiplexer is basically looks at the message, who wants it. The message contains the thread ID, the forum ID, who was the author, what's the post ID itself. And there's basically a ton of different channels that we publish the information on because this guy doesn't know who wants it. It's a general consumption platform. So this was a really great decision because it turns out other people inside the company were like, oh, I could use that information. And they wanted to subscribe to it too. And then the publisher publishes to Redis PubSub. And our keys look like this. They're really simple. Yeah, the average time is about 0.2 seconds. And most of that is I.O. on the queues and the fact that there's just a ton of green threads doing a ton of things. So there's a lot of I.O. Let's see. So one thing that was interesting is queue maintenance. So I mentioned high availability earlier. What happens if something blows up? Well, we want to deliver those messages still. So since the queue is just Redis, it's really nice because you can actually do like random access into it. It's just, like, oh, give me that one. So what we end up doing is every backend node is doing it says, oh, give me the data that's more than 15 seconds or more than 5 seconds old. And let's re-put that into the queue at the front of the queue such that it can be processed with higher priority now. Because if it's more than, again, 0.2 seconds, if it's older than that, it's probably been dropped on the floor. So, and we actually say if it's 15 seconds old, that's not real time anymore. So let's just not do it. Or the other thing that we have the ability to do there is we can count how many times a message has been canceled. So if a message fails too many times, maybe it's got broken Unicode or something. And maybe I don't handle that. I don't know. For whatever reason, it caused an exception. We can quarantine that message, inspect it later. Let's see. So yeah, just some lessons from Redis. We had to separate our PubSub nodes and our non-PubSub nodes. And we were finding that we were having such massive PubSub traffic that other transactions were kind of suffering as a result. Even though we were able to increase the load on PubSub more, was not affecting the PubSub system at all. So we separated them. Things were happy again. I wish I had numbers on this because it's really anecdotal right now. But the problem went away, so we stopped looking at it. Yeah, the other thing is when I said this queue maintenance thing, those are done as transactions. And the queue is also mutating. And so the problem is the way that the Redis library does transactions, you can do retries. And since we have so many processes doing this maintenance at the same time, because I figured, hey, well, it's idempotent. The only thing that will happen is at the end of any of these operations, the queue will still be clean, right? It will still be up to date. So excellent. Everyone can do it all the time. But it turns out the transactions were actually stomping on each other a little bit because they were trying to mutate the same state. And then you end up kind of getting a lot of these I.O. loops that cause a little bit of queue backup. So what we're planning on doing is actually using Zookeeper which provides election algorithms. You can just say, hey, am I the boss now? And it will say, yes, yes you are. And using that to determine who's in charge of queue maintenance. So there's only going to be one maintainer at any given time. And this is what the maintenance looks like. It's just calculate how old is too old, and then the feed is actually, or the queue is a Z set. It's a sorted set, sorted on insertion time. So just take them out, and then Thunk has this great little cancel thing that's like, hey, I'll do the rest of it. So that's just, hey, everyone, make sure that you're being actually processed. Also, I like gEvent a lot, and one of the things that's a problem with gEvent is that you can spawn just like a million threads. You can just have as many green threads as you want. And that's not actually a problem. That's why it's so powerful. And so we ended up having thousands, and then as the system evolved, hundreds of thousands of green threads doing stuff. And so we tried to make a thing that could, keep track of them. It's like, oh, okay, oh, you need to be restarted. Now you need to be restarted. You need to be killed. And that turned out to be impossible. So we actually just made something that we want to make it so they can maintain themselves. So the code's too big, so I put it up on GitHub. It's a short link, bit.ly.com, gEvent spawn. Basically, the watchdog says, given a way to restart things, or given a way to determine if something should be restarted or killed, I will make sure a thread continues operating under those rules. And then the time-sensitive backoff is basically the rules that we made. So it's exponential backoff. And basically, if something occasionally fails, it's probably OK. But if it's failing instantly a bunch of times in a row, it's probably dead. So the time-sensitive backoff is supposed to handle that. So it's like start, fail, start, fail, start, fail, kill it. And then there's also code in there that basically will halt the entire system. So you can say that this thread is critical. If it fails, kill everything. This thread is not critical. If it fails, just continue with life. So those are all very interesting, I think. And then one other lesson from gevent is if you need to just yield your thread, it's a sleep 0. It doesn't have its own command. It's just something I learned. All right, the front end. Our front end needs to be very fast because it's lots of transactions a second. Its job is to pool the Redis connections because, as I'm about to show you, you can't maintain an infinite number of connections to Redis. At some point, you have to start coalescing those resources. And then it also is responsible for just routing messages. This is highly available because they're just web servers, and HA proxy will just route your request to another one. Since it's real-time data, there's no state at all in this. It's just like, oh, it died. OK, this one. Take server 2 now. It's like it will work just as well as server 1 did. All right, water break. OK, so servicing a new request. The green arrows are basically kind of the back channel of, oh, a new request happens. It comes in, Flask says, oh, yay, here's your request, and here's the URL it came in on. From that URL, we basically extract the channel. We say, oh, you want CNN threads, or you want this specific thread ID, not the whole forum. And what that will do is that will go to the subscription pool and say, here's a request. Whenever anything comes in on this channel, make sure I get this information. And it ends up returning a queue to that request. And under the hood, we're basically using that queue to make a generator. So you say, while there's stuff in the queue, return it, or yield it. And WSGI servers can use generators to stream data. It's awesome. So that's that. Then the other direction, the listener receives a message. So it's like, oh, I got a message from Redis, and it was on channel CNN. So it tells the pub, it looks this up. The subscription pool is basically a giant dictionary. It says, let me get the channel for there. There are all the channels that need this information, and it just publishes that message to all the queues, and then those queues go out to the generators, and then it goes out back to the web clients. The front end holds connections for a really long time. Currently, it's like a minute and 30 seconds, so 90 seconds. I'm looking to make that 300 seconds, and I want to eliminate the timeout entirely. I want to just hold it open for as long as it will. Because long polling is basically, who here knows what long polling is? Yay! So you know that when there's data, you close the connection, and then the client opens another one. The thing is, again, the requests per second is what we're trying to minimize. So by never closing the connection, we can just yield data, and we just new line delimit that JSON. So it's just as long as there's data, we'll new line delimit it, and that will stay open forever. A lot of people ask, why not WebSockets? And I'm like, oh yeah, they're cool. Why not them? Because they don't work yet. And they're basically not stable. They're not in all the browsers that we want. Even though the DISQUS 12 version, I think all of the web browsers do support WebSockets, in some of the browsers, they're behind switches. There have been zero-day exploits, and Google said, nope, turn that off. And we can't risk that with our product. We can't put our product at that risk. We are going to use them, though. They're going to be in version 2. We're going to have them as the first choice, and if they're not there, it's going to fall back to this long polling-ish system. So we're going to be able to use that as a way to optimize the connection. It's going to be awesome. So this is what the generator that gets returned to the Flask, it's Flask or WSGI server looks like. There's a timeout, and again, 90 seconds right now. and then as long as there's data, yield it with a new line. And then once the timeout fires, unsubscribe yourself. It's really simple. But this is what it used to look like. Oh, actually, wait. One tip, it has to be application JSON. If you do like text / something, the browser will buffer it. So, or someone will buffer it. Application JSON gets through. So, all right, so this is the way it used to work. It used to be super simple. Get a pub/sub object and subscribe to the channel and then return the channel. And then just yield on the listen. And this works really fantastically at lower scales. We had like one server with 60,000 concurrent users on it doing this. But when we had 14 servers doing it this way, it turns out we just blew up Redis with 1.5 million connections. So we had to do something else. We have to pool the Redis connections because having a 1-to-1 ratio of sockets to open connections just did not work. So we ended up doing this pooling thing. So basically, I have this listener. So this is in the front-end stack. This is the listener thing. It has this pipe, which is just a queue. And when the new requests come in, they will simply put a tuple on the queue. And they look like these two at the top. Just a command, what do you want to do, subscribe or unsubscribe, and what's the channel you care about. So the listener is constantly listening for data from the Redis pub/sub connection, and we handle it. So there's code that goes there. And then after that handling occurs, if there are messages on the queue, let's process those. So get the action in the channel, and then just apply the action to the object. So basically, since we are constantly handling messages, we have such a high volume of them, this works really well. We don't need any maybe you didn't hear a message we don't in a couple seconds, time out, so you make sure you flush your pipe. But we have such a high volume, we don't need that. So it works really well because the pub/sub objects are not thread safe. So you can't mutate them at all while you're doing a listen. They're I guess, like half duplex or something. I don't know. But it's basically saying, it's waiting for Redis to return, hey, here's the data that you're listening for. And while it's doing that, it will not accept anything else. So this works fantastically. We went from a couple 100,000 connections per Redis node to like 1,000 total. And so everything's super fast now. So I've said some things about timeouts. Timeouts are great when you're expecting data. So you're like, oh, if I'm not listening, or if I don't get what I'm expecting, then I need to have an error or something. But it turns out that we were using timeouts for reclaiming resources. And it turns out we weren't actually getting anything back from those resources because when a timeout occurred, yeah, we got some memory back, but it also caused a CPU hit in the terms of that reconnection. So we decided that we basically want to maximize our cheap things, or maximize the usage of cheap things, so we can have lots of these super idle connections, going back to the heavy tail model. So we have lots of idle connections. We can hold those open forever. They don't cost us basically anything. But new connections are expensive. So getting rid of timeouts and lengthening our timeouts has actually decreased our CPU usage overall by just having a higher concurrency number. So that works great. Yes. How do we know that it worked? So in testing, I mentioned way in the first slides, we did this dark testing. So basically, you have a large cluster that's designed to be, true web scale, or true scale, I like that word. So it's supposed to be a huge scale. How do you actually load test that? Well, we could go to Amazon and spin up 60 or 100 nodes and hammer it with data. Or we could use our existing clients that are already deployed all over the internet by just telling them, hey, even though you don't have this feature enabled, use the network part of the feature, but just don't display the results of that. So that's what we call dark time. We use a switch library called Gargoyle that we wrote. That's open source. It's fantastic. And that lets you just turn features on and off. So at any given point of time, I'm just saying, ooh, let's see what it looks like with this code deployment and 50% network. Now 20% of our network. Now 90% of our network. And so just because I have that knob, I can just say, oh, let's use all of our deployed clients as the test cluster. It's great. At the beginning, though, when it was less stable, we definitely got a couple of users that noticed that there were these 404s occurring that wasn't affecting their experience, but you cannot hide them from the browser console. So if you are going to employ client load testing techniques, you really need to be careful about that. So yeah, that was just one lesson there. Then there was darkest time. This is the simulation of a single thread. So where we said we need 1 million clients to all simultaneously hit the same thread for information. It wasn't until we did this that we really discovered a lot of flaws in our architecture. So this was just a really great tool for, in both ways, to be able to test the entire system without, very quickly. I can just flip a switch and bam, they're doing it, without costing really any money. Like 60 nodes in Amazon, it's not cheap. So the lesson here is have knobs you can twiddle. You just don't want to have to do a deployment to get this information out there, nor do you want to have to do a rollback or another deployment to turn the test off, especially when something goes wrong. You want to be able to say, kill it with fire now. So stats. How do you know your testing worked? Well, you need to measure it. So I measure basically all of the things. Everything is timed. Everything is counted. It all goes to Graphite at the end of the day. It's super, super useful, especially when your numbers aren't what you think they're supposed to be. And it's really the most useful when two things that are supposed to be counting the same number have different numbers. So basically, by measuring what I thought was the same thing, how many clients are connected to Redis? Well, Redis has a different number than my application does. So what's going on there? You kind of like, oh, it turns out this rogue code over here needs to be deleted. It had 6,000 connections. Why? I don't know. But another thing is testing is hard in distributed systems. So this is a simple distributed system, but gauges are difficult because you need to aggregate them. So if you can, express things as +1s and -1s. And I also like this library called Scales. It's if you know of, there's a talk by someone named Coda Hale called Metrics Everywhere. If you have not seen it, watch it. It's why you should measure things. He made a great library called Metrics, but it's for Java. So Scales is a API port of it, and it's kind of fantastic. So what are some high-level lessons? Do your work early. Defer work that you might never need. So basically, there are some things like in these idle connections, I don't waste time setting up some of the infrastructure for each request if it's probably not going to be used. We can do that lazily. Even though it's more expensive later on, there's a 5 nines probability it's not going to be used. So it's actually a huge savings overall. End-to-end acts are great. We use them. It's one of the reasons we use Thunk, because we can confirm things. Except they are also expensive to have to say, hey guys, we're done. But ultimately, if you want to have that data reliability, they're great. Greenlights are effectively free, so use them everywhere. They're just like free threads, and they work awesome, and they're only getting better as gEvent moves to better backend libraries. PubSub in Redis is also effectively free. It's published to all the nodes. If no one's listening, it just disappears. So use it, abuse it. It's great. And it turns out other people in your company might want that information. And so I had a lot of people that were super happy that, like, I can just listen to all the messages. Yes, you can. So yeah. All right. One lesson from Nginx. You need the green line if you're doing real time. Proxy buffering off. That's just really important. Currently, we use Nginx as well for our gzipping. But again, not scalable. It takes up like 20% of our CPUs or something. Yeah. So libraries and links to them. I highly recommend all these things. Some special thanks to everyone at DISQUS for hiring me and letting me do this. Our DevOps guys, because I just wrote the Python, they're the ones that figured out how to make it so a kernel can handle like a million connections or something. I don't know. And Jeff, he reviewed literally all of the code. There's a lot of it, so thank you, Jeff. So this is my question slide for you, because these are our open questions. So what is the best system config for handling like 40,000 requests per second? I don't know. How do we make the front end faster? Because I need to make it faster. We're using PyWizzy right now. I'm looking at like FAPWS, which is a horrible name. But I'm looking at that. It's written in C, and it has asynchronous in the name. That's fast asynchronous Python web server. Libevent to libev. Gevent 1.0 might give us some speed. I don't know. Dumping WSGI for raw sockets is our last resort. Just we don't need that stuff. We have a very controlled system. It's an internal API. And then also, what's the best internal option for Python PubSub? Because currently I wrote my own thing, and I don't know anything about PubSub other than I consume the Redis API. So discuss. Also, we're hiring. Thank you.
Yeah, too many questions at a time.
Lots of questions.
Once.
My intent for this part was not to just have me answer questions, but a lot of people raised their hands that said they have real time. So maybe I'm just the guy at the front of the room, not the guy with all the answers. So I like open spaces a lot, so I encourage that.
So I've got one question for you and one suggestion. Suggestion earlier on, maybe in between WSGI and raw sockets, you could consider 0MQ.
So we've talked a lot about 0MQ, and I wait. So for what part of the system? This is so WSGI for raw sockets is actually the incoming requests. So 0MQ from JavaScript to Python is what you're suggesting?
I wasn't completely clear on what point these things are coming in. I thought that was more of a controlled environment. So.
No. So at the WSGI part is actually our front end API, the front end server that goes across the internet to a web browser, where the embed is, so the embeddable JavaScript is ultimately the main consumer of the front end. So it needs to be cross language like that, which I don't think 0MQ is. Right.
And another question I had. Why Flask if you're so experienced with Django?
This is a great question as well. I didn't need any data storage at all. I needed something that's going to just get out of my way, and Flask is good at that. I use it primarily for application organization even. Jinja's not used. I just use it as an abstraction to load the routes and some ease of use there. I use blueprints for the endpoints because the endpoint's highly generic. So you have like your thread endpoint, your forum endpoint, your user endpoint. They're all basically the same. So I use blueprints to just load the same code multiple times there. It's basically just for organization. No data source, so that's the main reason.
Great, thanks.
Thank you.
Question here?
There's a bunch of all over the room. We use two? Or?
About WSGI, do you know about UWSGI?
Yeah, micro WSGI, or UWSGI. I've never used it. It's built into Nginx, right?
Yeah, the author is here actually, so you want to talk to him. Not in this room, but around here. So I would suggest you do.
All right, we'll look at that one. Cool.
Yeah.
I like, one thing I do like is not being tied to Nginx. Actually, another question is, do we even need it? Has anyone here ever just run like Gunicorn like to the raw internet, or do you have to have that buffer? Like we have HA proxy and Nginx, and I'm like, do we need those? I don't know. Yes, you do. Okay, thank you, David.
So you mentioned you were testing out and load testing things using a dark launch, so you could just have a knob and turn things on and off.
Yeah.
Do you also have that in case you get a sudden launch of traffic? So for example, turning off the user is typing thing, or anything else as a big red button in case you get a lot more traffic than expected?
So currently, so how many in here use Gargoyle? Okay, you guys should all check out Gargoyle. It's got a JavaScript implementation as well as a Django one. So all of the knobs are actually in the client side and not the server side right now. So I'm working on enabling it so we can turn off features in the server side. But to your question, the answer is yes, we can turn off them in various features in the client, but we could not protect ourselves from an attacker that was like, I'm going to spam the hell out of his typing right now. That would take us down. Or not, because it's totally web scale.
Was there a question in
There were
this
questions
side?
in the back, I think, and front.
So you're streaming the updates to the client with sort of separated by line breaks.
Yes.
I'd not seen that technique before. For me, long polling is you wait until there is data and then it disconnects.
Yeah.
So there's a couple of questions related to that. How is it processed in JavaScript? And
a great
is there a gap when it times out and it's reconnecting where it can miss any updates?
All right, so the first answer is you will have to ask Anton, who's at value of on Twitter, and because I don't know anything about JavaScript, so that's sadly I can't answer that. But as far as I understand, though, an AJAX request does allow you raw access to the data as it comes available. I don't know anything more than that, though. The next question, can you repeat again? I forgot.
So your Redis pub/sub pooler is putting things into a queue.
Yeah.
And presumably when the timeout happens, so that's, you said every 90 seconds.
Yeah.
The client disconnects and then reconnects.
Oh, yes. Okay, so yes, you can miss messages. It takes actually up to a couple seconds to do a reconnect. And as I was saying before, Redis pub/sub is totally ephemeral, and we do no buffering at all. There's no caching of anything. It's just if you miss a message, you miss the message. So we overlap the requests. So the client is aware of how long the request is going to take, and it starts the second request about 10 seconds before the previous ends. We're looking for better ways to handle this, such as not timing out, and also WebSockets should allow us to have a much. I don't think browsers will time out a WebSocket connection, but they will ultimately, like Chrome will just kill something after a couple minutes. So we're doing that overlap right now.
And does that go through weird and wonderful proxies in, say, China or something?
Oh, you mean like where's all the data flowing through?
Well, there's always some weird HTTP implementation that, is going to buffer up those things, and does it sort of...
Oh, yeah, no, this is totally susceptible to that Cisco router that you thought was a Cisco router, but it's actually a knockoff from China, and it doing something weird. So the stream could potentially be broken or screwed up in a whole bunch of ways. But turns out the internet usually works the way we expect, which is really surprising. So
I think you jokingly mentioned Node at the start.
Yes.
But I was wondering, did you try any other implementations?
Node is what my CTO wants to try next if I can't make this faster. So, but when we were starting out, no, I pretty much started with gEvent, and it was working really well. So I'm just this works great. I'm going to just keep running with it. So there was not a bunch of exploration done. I guess we looked at Eventlet as well, I chose gEvent because it does less, and most of our using of gEvent is at low levels. We don't use pooling ever. We don't use a lot of those things that normally you want from an application. But this whole thing is, no throttle. So we want things to be fast, and we spawn tons of greenlets everywhere. So gEvent works well for that, just because it's a smaller library.
So first suggestion, and did you consider using Socket.io for and gEvent Socket.io for the front end?
Did you say Socket.io?
Yeah.
No, I don't know a whole lot about it, but isn't Socket.io
some kind of abstraction? So if the browser has WebSockets, it will go through WebSockets. If it doesn't, it will go to long polling or something.
Yeah, and then there's a node-based proxy for it, basically, right? So you have the Socket.io in your client end, and then you have a node server.
And you have Socket.io with gEvent on.
I didn't know it existed. So cool, I'll check it out. If that does the degradation
we are using
for us.
it, so maybe you should just go and check it.
All right, yeah, that's definitely worth looking at. Cool, thank you.
And the question I have, did you consider making the channels in Redis per user, not per resource?
What do you mean?
So you publish something for user ID and then the resource for him.
We actually publish just on a ton of channels. So when the message goes out, that message gets published on like between 5 and 15 different channels, including per user, per thread, per ID, per forum, if it's a reply to a message, it goes out on like the post ID of the message it's replying to, of the user ID of the author that it's replying to. So you can really subscribe to all sorts of permutations of information here. Currently that's not accessible in the API, but that's coming in version 2, so you could say, hey, I'm interested in these 50 keys, make a custom subscription for me. Does that answer your question?
Sort of. That's okay.
Hey, well, we can talk more about it when everyone leaves.
Thanks.
Hi. You said you use graphite for graphing. Isn't it a problem for you that the older or the longer ago the graphs are, the less detail you have because of the nature how these round-robin databases work?
Yeah, it's a huge problem for me. Luckily, it's a new service, and I don't have a lot of data in it. But one anecdote was I was definitely having some problems with it, and I was trying to compare my traffic from that day to a month ago, and it had not generated the bucket yet. So apparently on a month scale, so they're like 6-hour buckets or something. So I had to wait like 2 more hours until I could see that data appropriately. So I don't like graphite personally. We're looking at we're having an internal stats library that we're working on that should be able to be non-restrictive in that manner. And another library I like that solves this problem is TSDB. It's by StumbleUpon, and we might try that one as well. But when you're invested in an infrastructure, you use the infrastructure you have. So that's the only reason I used it. But no, I believe in keeping data forever and all of the data. Every data point's important.
Hi. You mentioned, well, obviously you're using Redis for the whole queuing thing. Is it just operational familiarity with it, why you went with that rather than another queuing system?
Yeah. Well, there were basically 2 important things I needed. I needed PubSub and I needed a queue. And Redis is the best PubSub right now, I think. ZeroMQ also provides PubSub, but I like brokered things because, like I said, measuring distributed systems is hard, and having a broker makes it not a distributed system anymore. So now it's easy to see how many messages are occurring. You can log into the server and you can query, oh, look, this is what's in the queue. I don't have to do, I have no idea how you would even say, what's the local queue on every PubSub node in the system. So that's the reason. That's the first reason I chose Redis. It was PubSub was an operational requirement, and then why we use it for the queue was basically we were already using it. So another thing about systems is the fewer moving pieces, the better. So if there was only one data store that we had to keep at operational at a highly available level, that's great. If we also had Redis, or Rabbit or something, that would be 2 HA systems we would have to build. And again, our HA around Redis is interesting. We don't have any. It's we use Nidus, which is a library that we wrote. David, did we write Nidus? Yeah. All right. Yes, that we wrote, and it's open source on GitHub, and basically it does consistent hashing. So the Redis nodes are all arranged in a ring. And if one of them disappears, the ring shrinks. And because it's PubSub information, it's okay. Nothing's actually lost because every front-end node is connected to every Redis node and has subscriptions registered. So nothing actually changes. It's kind of some timeouts will occur in the Redis connections. They'll simply reconnect to the new nodes. What's that called? Nidus. Nydus. I think. Yeah. So consistent hashing for the win. Though I would like to have HA. I would like to not have those things. I think that the maximum downtime a client would see is 30 seconds if a Redis node went away.
Can you give us some numbers on how many data you serve in the real time, in the peak time? So how much is it?
How much? Oh, in terms of like megabytes?
Yeah, something like that.
That's a great question. I have no idea. That's another thing to measure. But I will find out for you. Because actually, it's a fun story. When we were doing the dark time testing, we had our, we have this all in a data center. We don't use Amazon. So we actually saturated our links when we were doing the dark time testing because we were sending so much information from the back-end nodes to the front-end nodes, and from the front-end nodes to the internet, because this was the first time we had seen the massive replication of actual messages going out instead of just having a million people sitting there listening to the internet as normal. So this is when we started learning that we needed to turn gzip on, that we needed to move the compression back so we weren't doing gzip 10,000 times. But ultimately, more than 10 megabits, I think, is what the link was. And then compressing it freed up space. So I know that we saturated the link.
So where does the decompression happen? Is that in
this is so the web browser ideally. So here's the problem. It would be awesome if you could just gzip each message, send it across, and then have the web browser understand, oh, it's compressed, and let me uncompress them, which is how gzipped encoding works. So what our goal is, we want to make a stream of a gzip chunked encoded stream that we can actually spread, like when it's going to be streamed over Redis, or maybe not, maybe just a socket. This might be different. So streaming that over something to all the requests. And then the idea is that it's a gzip chunked encoded stream that if you set the header type to gzip chunked encoding, the web browser will handle that. The problem is doing each message once is not actually chunked encoding. So you would have to do that in JavaScript. So we're looking at things like, well, why actually even use JSON? Is JSON the best thing here? Protobufs work in JavaScript, so maybe we could do compressed protobufs. So there's a whole bunch of options of what the data type is that we actually send out, because JSON is not efficient. So that's my mixed spiel on compression / encoding, I guess. But the goal is to make a stream and have the browser handle it, because we don't want the JavaScript to have to.
So when you do your testing, how much faster can you make the system go, and how are you going to make it meet the expanded demand over the next year or so?
Great question. So we were operating the cluster of 14 front-end servers at about 90% CPU for about 20% of our network. And what we ended up, so one optimization was the timeout change. So by having the connections held much longer, we saw it go down to, it wasn't 90%, it was about 60% CPU, I'm sorry. So it went from 60% CPU to 20% CPU by simply changing those, twiddling those knobs. So there's no obvious low-hanging fruit still, but I think that we can do a lot in terms of still moving the gzipping fully to the back end. Taking that out of Nginx is going to be a large win. For the IGN event for E3, when we had it was tens of thousands of users on one thread, we were seeing the machines about 20 to 30% gzipping. So moving that out is going to be a huge win, and otherwise I think that I can at least double the performance still, based on what I've seen.
How many servers have you got?
Total? About 20, I think. Yeah, something that order. 22, exactly.
How do you ensure that new lines appearing inside gzip data do not break your framing?
I don't know. I'm just using a libgzip or something, so it's just, I'm not new lining in between the gzips. That doesn't work at all. So it's basically, the experiment that I've done with the gzip was I gzipped a message, and then I did do a new line, but that is a gzipped thing in and of itself. The client would get it and run, like, there's JavaScript gzip implementations that use all your CPU. So, so you would ungzip it in the browser as an entity. Using more than, like, so does that answer your question? I mean, I guess I don't know enough about frame transports beyond that to answer.
Well, you showed us code that sends messages separated by new lines. And then you mentioned gzipping.
Oh yeah, the new lining would have to change. The goal would be here. So the goal here would be, instead of actually yielding a new line at this point, is it would be getting the data from the back end, which is already correct. So you would basically say, this is a data stream that needs to be replicated to the clients exactly. So we would remove the new line at that point. And it would be, so, I mean, when you do chunks encoding, you're sending a chunk of data, right? So whatever that protocol says, put it in here. We can talk more.
Have you looked into reducing the size of the HTTP headers sent and received, such as by using a cookieless domain?
No. I'll write that down. Reduce header size. Yeah, there's a lot that we can, there's a lot of unnecessary data being sent even in just the JSON objects that we're sending. There's like, I guess so, yeah, this is low-hanging fruit. We're sending like 10x the information that we need just because I thought the front end could do something cool with it. And there are a couple of features that did not exist. They said, oh, we want to do this thing. I said, well, I can tell you if they're typing. And I'm like, oh, cool. No, wait, that's a bad example. That was their idea. But there was something else. So that, having extra information, like removing spam messages. I say, hey, here's information and it's spam. I mean, I guess I could just not send the entire message. That's a huge option. But so there's stuff like that. Or here's a message and it was previously approved, but now it's been moderated. So remove it. So that's information that you don't need 100% of the time, but it's sent 100% of the time. So there's lots of more options there.
So I'm a DISQUS user and I use page speed. And all my pages without DISQUS have 100, and those with, it suggests me to change your JavaScript. And I think it offers me for download a better version. Is that a false alarm?
Page speed, you said? Okay, well we need
Google service.
So yeah, so we real-time does have an issue that it looks like something's really slow, but the same is true if you go into
JavaScript itself. It says it could be compressed.
Oh,
you remove some things and it's smaller.
I'm being told no. Yeah, we minify and do a bunch of things, and I think that we. I don't know.
Okay.
Anton's really smart. I believe in him.
It suggests me to minify this all the time.
Interesting.
If it's a false alarm, it's okay.
I'm saying false alarm, and if it's not a false alarm, we'll fix it.
So there's been talk of compressed headers and WebSockets. So does Speedy fit into this somewhere?
No, well, I don't know. What's Speedy?
The Google thing, the HTTP and a single connection, and you can multiplex HTTP components over. If you use Gmail on Chrome, you're probably using Speedy right now.
Well,
SPDY?
SPDY. I'll check it out. I don't know anything about it, though. It could be awesome.
It's kind of cool.
Yeah. SPDY. Are there any more questions? No. Well,
I think we are done. Everybody needs a coffee. Thank you. Yeah. Thank you very much, Andy.
Thank you. Hey, code.
Okay. I would like to remind you that this evening there will be the